So today we're going to be talking about what's called moments. We're having a moment, some moments, and expectations of random variables. All right, we've got these random variables. We looked at their distributions. We're going to continue looking at their distributions, but today we're going to be talking about measures or metrics for describing these random variables. Something that you all know, but we're going to take a deep dive into something called the mean and the standard deviation. So first we're going to define moments and expectations of distributions of random variables. We are going to derive and calculate these moments. Quantitatively to describe the distribution of random variables. And the idea behind that is and we'll talk about it like the central tendency or central value, like a mean or a median, what's the spread, standard deviation. And then we'll ultimately, and we might not get to this today, it might be on Wednesday, but we'll compare the moments of PDFs. So again, PDF is just probability. You can use it two ways. We'll say probability distribution function or probability density function. Density only works with continuous variables, but you can also use this to describe the distribution of discrete and continuous variables. So distribution just kind of means what's the spread, right? Or it could be discrete. So moments of PDFs to their shapes. Wide rule. I was obsessed with college rule in like, I don't know, middle school, high school. When did you start writing in those notebooks? Middle school. Yeah, college rule was like, that was where it was at for me. But right now I need the wide rule. I'm back at wide rule here. So the first thing we're going to talk about is our central values of random variables. And this is basically just a way to summarize a random variable. We've got we'll just go to the distribution of the sum of two dice rolls. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then this would be, we'll just call it probability. And I think does anyone know what the probability of the 7 is? It's like 6 out of 36, right? So what is it 7 out of 36? And so what is that approximately? Yeah. So about 0.2. So a little under 0.2, so 0.2. Okay. It was 6, okay. Well, you know. Okay, and then it was like 1, so 1/12, right? I think for each of these or 136 for each of these outcomes. Oh, sorry, 1 is a non-day, you can't do 1. Starts at 2. Anyway, so you get this distribution, right? And it's symmetrical. And so I've got different ways of describing this distribution. We talked earlier about kind of calculating probabilities. But now we're going to think about ways to summarize this. And when you look at this, what are some ways to summarize this? If you want to say, okay, I'm thinking of my random variable, it's the sum of 2 dice rolls. How could I just kind of, so I can represent it visually, it's got this symmetrical distribution, but what are some other ways we could summarize the data? Think of the summary function in R. Do you remember using that? Yeah. So I'm just like, I don't know why I was shaking my head, but yes, that's what. Am I wrong? I was like, yeah, totally. Sometimes you shake your head in a way that, yeah, anyway. Yeah, so summarize, so you could do summarize in R, and you could say this was like the distribution of all the potential outcomes, right? And you would get a lot of different things: mean, median, standard deviation. You get the different quartiles. We'll talk about those later. Sorry. These kind of tell you what values are extreme and what values are central. So a central value could be a mean. Or a median. I don't know why I keep trying to do this. That would say, okay, well, on average, we expect to roll what? A 7, right? And that's just because this is symmetrical, right? The mean wouldn't necessarily lie in the middle if this wasn't a symmetrical distribution. We'll look at that in a second. So we've got the mean, and we're all kind of vaguely familiar with what the mean is, right? It is also known as the expected value of X. Why do we say expected value? Yeah, and like in probability theory, expected value, which we write as big E of X, expected value is equal to the mean. Or we'll write it another way, we'll write it as mu. And this is kind of a theoretical mean. So expected value, if I roll 2 dice, I get a 7. What's that called? You rolled in a game of craps. It's craps. I think it's just called craps. Yeah. So you roll a 7, it's craps, so you lose, you don't win the bet, everyone else on the table loses. There's a big groan, but you got a 7, you kind of expected that, right? So we expect the expected value is the value you expect to see, generally speaking, on average over time. Of course, you could get any number of these things. So the mean is the expected value. And for what kind of distribution is this? Continuous or discrete? It's a discrete distribution. So what do we call this distribution in terms of what kind of distribution is it? A probability mass function, a PMF, so probability mass. And we say mass because we can read directly the probability off of these values. And so mass is probability. Density, we have to do this integration to get the probability back out of it. So for discrete random variables, the expected value of x, which is again is the mean, is just equal to, and we've done this probably all the time, right? But this is just a big, mathematical definition, is equal to the value of x times the probability of its value. And all of this is going to be equal to, if we base it off the theoretical distribution, is going to be equal to mu, so the mean of the population, I guess we're probably used to calculating the mean as summing everything up and then dividing it by the number of observations, right? But if we have a distribution, you actually get the same answer this way. So the probability of x times the value of x. So this is basically a weighted average based on the probability of it. So the way we would do this is 136 times 2 plus 1, I guess it's 18th, times 3 plus 1/12 times 4, etc. And then you sum all those up, and then guess what? You get 7. So this ends up being a probability weighted average.
So I've seen in some books like you got to reduce capital, but then in some books they want brackets, which they said are essentially the same as parentheses. I'll select to use a big X, or can it be?
Yeah. So this is technically a big X because what does this big X represent? The total the random variable that kind of summarizes everything. So every potential value, and then little x is a manifestation of that. So little x is that sum of the dice rolls that you just did. So this is all technically big X. I am not great at keeping the notation the same all the time, so I'm going to introduce it, and then I'm going to have to let you guys. You're welcome to ask questions, and I appreciate those questions. But yes. So this is little x of I. This is just a particular observation that comes out. Okay, so that is the basic definition of the expected value. I will also say that this is based on the distribution, the theoretical distribution. This mu is the mean of the population because this distribution represents the population, the total, the complete distribution of observations that we could have. If we had for samples, so if we did 30 rolls, right? We could calculate the mean just by doing the sum of the rolls, or the sum of the values that we get for each roll divided by the number divided by 30. But you would get the same answer if you made a distribution like this and just did the probability or the frequency, right? The relative frequency times the observation. So we did 30 rolls, we got 5 7s, 4 3s, etc. But what that ends up being then, is we end up getting expected value of x from a sample. This ends up being what we call x bar, which is the mean of a sample. So we're going to go back and forth between mu and x bar a lot. Mu means the theory, which is 7. But if you did 30 dice rolls and did the sum of it, you probably wouldn't get 7 as the average. It's probably close to 7, but it might be like 7.5, right? So that's why we say x bar, the mean of the sample. Yeah.
Also works to call x bar and
Yeah, that's a great way of saying. So a parameter is of a theoretical distribution, the theory, and then a statistic, which honestly we haven't really gotten into statistics yet. We've been doing probability theory. A statistic is something based on data, some metric based on data. So let's just do this for continuous variables. I'm just going to write it out. The expected value of x. And we'll note that we did the sum, right? So if we're continuous variables, that means we're going to be doing an integral from negative infinity to infinity, unless there's some real bounds that we introduce on that. And that's just going to be x times the PDF function of x. So we're weighting each value of x by its probability density function. And this gives us the what we call, so it's expected value, but it's also called the central moment. Or first moment. So I'll explain that in a second. But this is a very simple equation we can use if instead we don't have a sample that we can just very quickly calculate the mean of. We have a distribution function that represents the data, or say we think the data represent a certain distribution. Then we can very quickly find the expected value or the mean based on this distribution function for the range of x's that we're interested in. We might swap this out with a 0 if there's, our function can't take, or our random variable can't take on negative values. So why do we call this the moments? Or why the central moment? I'm sure everyone's on the edge of their seat about that. If we just look at a particular distribution, I'm just going to draw a generic one. So this one's not symmetrical. Where would you say the mean value is on this distribution? Is it going to be in the middle? No? Where do you think, Ryan? It's going to be slightly over here because we've got these extreme observations over here, right? These kind of, you call this kind of a thick-tailed, we'll talk about that more later, but thick-tailed distribution. It means it has a lot of observations. It has some probability density far away from the mean. So another way to think about this is, where is the center of gravity of this shape, this area? And that center of gravity, if we were to take just any generic shape and find the center of gravity of it, it's going to line up with the mean value. We'll call that distance along the x-axis to the center of gravity. We'll call that x naught. So distance to center of gravity on x-axis. This is in statics, right? You guys see this in statics?
Oh yeah, like centroid.
Centroid. Yeah, so this is center of gravity centroid. And then just the generic definition for a centroid in the x direction is equal to the integral of x, whatever that function is, dx, divided by the integral of the function itself. So this is basically just from statics or from the math of finding the center of gravity of a shape, of a two-dimensional shape. So f of x is really the PDF function, right? Because now we're in statistic land. So this is our PDF. That's our generic function in there. And if we integrate a PDF, we get the area under the PDF. What do we get? Well, yes, we get the CDF if we integrate up to some variable x, and I'll show that in a second. But if we integrate and we do the area under the curve, which is integrating the PDF, yeah, you get 1. So this is equal to 1 if we just integrate the PDF. And so we end up with x naught is just equal to x f of x d of x. And sorry, I didn't mean to write that down there. Which is equal to the central moment or the expected value of x. So when we say central moments, moment about the x-axis, that's kind of terminology from statics and mechanics. And the mean mathematically is the same as the distance along the x-axis to the center of gravity of a distribution. So that's why we do that. So central moment, and it's also known as the first moment. So I can give you an example. So say I say x follows, we'll say some function, right? F of x, and I give you that function. So that squiggly, that line just means follows. So x is a random variable, it follows some function. I give you that function, and I can say calculate the expected value of x or the central moment of x. And then what would you do to calculate that? You would just say expected value of x is equal to the integral, whatever the bounds are from a to b of x f of x dx. And then you would just do that integral. Plug in the values, and then you get your value. So very kind of basic Calc 1 stuff. So we know that the mean is not necessarily in the middle because of extreme values. And what's another way to define the center of a distribution of data of a random variable? That's another metric that we can use. Median, I love the median. Median's really, I'm going to say, as far as central tendencies go, the median is my favorite. Can anyone define the median numerically? I think that is the way you actually calculate. If you have like a series of numbers. Oh, that's how you find. So you said n plus 1 divided by 2. That's how you find the position, right? Yeah. Yeah. So we know that it has to do with rank. And the median value falls in the middle, right? So it's the value of x for which 50% of observations fall above and below. So it's just sticking there right in the middle. And to find it, you can rank your data, and then it's n plus 1 over 2. And that would give you the position of the median value. Yep, exactly. So 50th percentile. And percentile just means what percent of your data fall above and below. So at the 50th percentile, 50% of data fall above and below. Well, I guess it should be what falls below. So it should be percent of data or observations that fall below. So the 20th percentile, and I rate it as p-tile, would be 20% of data fall below. 90th percentile, bigger value, right? Because 90% of the data fall below. You probably, took tests, standardized tests in high school and middle school, and they gave you your percentile, which I think is kind of messed up for kids, but whatever. Okay. So there's a lot of ways to look at the median. We'll go to a cumulative distribution function just because we're learning this still. So we have X, we have a CDF, goes all the way to 1. And it's usually some kind of S curve that looks like this that eventually, converges to 1. And what we're interested in for the median is the cumulative probability of 50%, right? 50% of the observations fall above and below. So this would be our median value. So saying that 50% of the observations fall below it is the same thing as saying the cumulative probability is 50% or 0.5. And why do we use the median value? What are some examples of, how about this? After you write that down, let's take a minute to talk about where the mean and the median would diverge and why we report one versus the other. Jaden, when you're ready, I can chat with you about that.
Okay, perfect. I think that it would mainly diverge when there are kind of like the other example, like extremes, like the thick-tailed, because that's going to pull the mean one way or the other, while the median might be more accurate, might be a more accurate representation of the data at times, especially in those extreme situations.
Yeah, exactly. Can you think of an example where you might choose one versus the other?
Let's see, probably, I guess, like even the income example would be a good one because you're going to have your, millionaires and everything that's going to probably skew it, and then have the people that are in like severe poverty skew it. Whereas a more accurate representation might be of like the median of the data.
Yeah, totally. So just like few extreme values, right? Skew the outcome. What did you guys come up with, Ryan and Sam?
So mean is more susceptible to the values are perhaps changing in particular amount, whereas the median is a little more resistant to change. It's more stable, sticks to its original position.
Yeah, stable position or value. Because it's, you have a lot of observations probably clustered around the center. And so if you add on, you're collecting more data and you add on some extreme big values or extreme small values, that median, it's going to be jostled around in terms of the order of its place. And so which value does it fall on? But it's not going to probably, if your data isn't really variable, it's probably not going to change the value that much. But the mean, you throw that, so Jaden gave the example of median income, throw in a couple, 6-7 figure salaries in there, and that can shift our central tendency value greatly. So another example of median home values. Similar thing, right? In Grand Junction, I don't know what the number is. Back in 2020, it was median home value. 2020, I guess I looked this up in 2020 and it was 260,000. But the mean home value, do you think it was bigger or smaller? It was bigger. It was 315. Right? We got a couple, not a couple, right? We probably have dozens or hundreds of multi-million-dollar homes, but most of them are, this has probably gone up a lot, unfortunately, because of everything that's going on. Making it harder to afford homes. So that's why we often report the median home value. Okay, last thing is we'll talk about is the mode. Hopefully you learned this in high school or something, right? What's the mode? The most common or most frequently appearing value. And we call it X tilde is the mode. And oftentimes it overlaps with the mean and the median if it's a symmetrical, but this is asymmetrical, right? So the mode and here, the mean's probably somewhere over here, right? But if it's symmetrical, then they all line up. I'm just going to call that symmetrical. You'll have to take my word for it. Here, the mode, the mean, and the median all line up. Okay. Let's go and talk now about the second moment. So we talked about the first moment, which was the expected value or the mean. And what do you think the second moment is? Just guessing. It's a measure of dispersion. Yeah, I think it's technically the variance, but the standard deviation comes from that. Okay, so this describes how wide or narrowly the values of a random variable are spread about the mean. Or the expected value. So what were some examples from the video that they talked about the spread or dispersion of the data? Arrival times? Okay. So how, when did a bird arrive, like a date or something like that, or time? What was another example? What's that? Yeah, different video maybe. Okay. Taco shop. And what were they measuring the spread of for the taco shop? Okay, so monthly revenues. What do you think a taco shop wants its monthly revenues? Do you think it wants to have a big spread or a narrow spread? And what would narrow mean for them? Yeah. Yeah, so big spread means we have extremes, right? More often you're going to have extremes. And then a narrow spread, it's going to be more consistent. Closer to the mean, right? We have an average income, and we think month to month, we expect to have close to that average that helps us to plan, rather than kind of feast and famine, right? Economies like narrow spread because that helps people plan. It helps you have a good tax base and know what that tax base is year to year. Grand Junction had a very big spread in terms of its kind of regional income, economic income, when it was mostly tied to energy extraction, right? So the oil and gas booms that would happen and then crashes. But our economy is still very tied to energy, but it's also tied to a lot of other things, industry, health, recreation, etc. So we're getting into a phase out here where our economy is the spread of our kind of annual income and tax base is narrowing. Okay, so let's do a little bit of mathematical definition of this. We defined our expected value of x is equal to the integral of x times the distribution of x across its value. But we could also say, what's the expected value of a function, g of x? We're just going to substitute x in for a function. And this is a very simple thing, but it's also pretty powerful. And what it says is that we can just substitute in that function, whatever that function is, and multiply it by the distribution of that variable. And we can get the expected value of this function. So this is essentially gives us a weighted average of that function. So for this second moment, we're going to let that function g of x equal this measure of dispersion. How far does each individual observation of x or realization of our random variable stray from the mean value? And then we're going to square that so that we don't get positive or negative values. We could also write this out as x minus mu squared. X bar and mu is the population, x bar is from a sample of data. We'll stick with mu because we're being theoretical here. So then now we can say we're going to define our variance of x. So var variance. And we're going to use this formulation by plugging in this for g of x, right? And we're just going to say x minus mu squared times the distribution of x dx. So this is the definition of the second moment of x, which is just the variance, and it's a measure of the spread. We can also write this as the expected value of x minus mu squared. Moves that up there a little bit. Now, do y'all know the relationship between the standard deviation and the variance? It's a square root. So so standard deviation of x, which we're going to write a lot of different ways. So the theoretical value, so the population value, is written as sigma. And then we rate it S for the sample or the statistic based on data, just based on a data set. And that's just equal to the square root of the variance. Why do we use the standard deviation more? Because I think you probably see the standard deviation more than you see the variance out there. Because, well, it kind of depends on how you define X. So if X is your annual revenue, then you're looking at year to year versus monthly, then you're just looking at the variance of the monthly income. What it turns out, if you look at the units, X minus mu squared, the units of variance are the random variable squared. So if it's revenue, it would be dollars squared. So we take the standard, if we take the square root of it, then we get the same units as X, our random variable. And that's just a little more helpful to interpret. So if that would be dollars instead of dollars squared. And then you can kind of interpret that as, okay, we'll talk about how to interpret standard deviation a little bit better, kind of when you look at a distribution, but that says, okay, my standard deviation is $10,000 versus $20,000. And then you can kind of compare that a little more intuitively as a statistic. Okay, let's just look at, got about 6 minutes left. Okay, so I'll let you know that we can normalize the variance or standard deviation. I guess we'll just say standard deviation using the mean to compare variance across different data sets. And we'll define the coefficient of variation or CV as sigma over mu. So the standard deviation over the mean. These both have the same units, and so this is non-dimensional or dimensionless. Dimensional. We can also just do S over X bar if it's based on a data set. And the way to think about this, I use it a lot when I'm thinking about comparing the variability of flows in a river. So if I have a big river like the Colorado, and I want to compare the variability in the flow in the Colorado River, where the mean flow is like, I don't know, we'll say 5,000 CFS, something like that, cubic feet per second. And I want to compare the variability and say S is equal to 1,000 CFS. To say, we'll pick the Canna Creek. Or no, we're going to go over to Boulder Creek, where the mean in Boulder Creek might be just, we'll say 600 CFS, right? And the standard deviation is 200. So I can calculate my coefficient of variation for the Colorado River and coefficient of variation for Boulder Creek. And that gives me a way to compare directly the variability of it, because it's just normalized by the mean. You basically take the mean out, and then you've got that variability. So in this case, we would get, this would be CV is equal to 0.2. And here the coefficient of variation is that 1/3, 0.3, right? So we say, oh, Boulder Creek's more variable. But if I compare the standard deviation, you're like, oh, well, the Colorado River's got a bigger standard deviation, but it also has a bigger average, a bigger kind of baseline. So that's a really useful thing to compare. All right, last thing we'll do, the 2 minutes that we have, let's just look at a couple different distributions and talk about their standard deviations or their variance. So we'll do distribution number 1, which looks like this. And then distribution number 2, which looks like this. Which one has a larger variance? And why do you say the green one has a larger variance? Uh-huh. And you think about this also in terms of where is the area? So that's all great. So where is the area under the curve? So the vast majority of the area under the curve is kind of near the mean, right? So, you know what, I don't know what percentage of this is, but say it's like 80% is like really close in. Versus if I look at that same metric over here, I've got much less percentage of area in that same, right? So maybe there's like 50% is there, and then we have 25% here and 25% here. And by area, that means we have a lot more extreme observations, right? And by extreme, it just means farther away from the mean. So we have a higher density away from the mean. And so that means we have larger variance, more extreme observations. And in this case, it's big and it's over here as well on the smaller observations. So you're more likely, because you have that area, you're more likely to see big observations and small observations versus observations that are closer to the mean. So in this case, we would say the variance, we'll call this PDF number 2, and they'll call this PDF number 1. So the variance of x2 is greater than the variance of x1. Just by looking at it spread out, you've got those thick tails, right? Great.